Hey everyone, welcome to the Chapter 4 vodcast. There's a lot of stuff that we need to cover. These are the following topics that we're going to look at in Chapter 4. What happens when things dissolve, reactions that produce a precipitate, net ionic equations, definitions and theories about acids, conjugate acid-base pairs, oxidation versus reduction, single replacement reactions, molarity dilutions and titrations, which is, well, a lot. So I decided to break down this particular chapter into 2 vodcasts. So make sure you know that you should be reading Chapter 4 alone by yourself and taking your own notes before you dive into this. So let's grab your guided notes, your calculator, and for this one we're also going to need you to open up your textbook. And let's begin. In sections 1 and 2 of Chapter 4, I consider this just a really good review, stuff that you should probably already know. Like a solute is the stuff that dissolves, solvent is the stuff that does the dissolving, all right, and just kind of basic ideas of what an electrolyte is. An electrolyte is any ion that is dissolved in a solvent that causes the solution to, well, produce electricity or conduct electricity. But here's the thing that I need to make sure you guys know. Not all stuff that dissolves in water is technically an electrolyte. You see, when an ion dissolves in water, it can produce or conduct electricity. And not everything that dissolves actually does that. Not everything that dissolves creates an ion. So for example, sugar. Sugar is a giant molecule, and all of the atoms in sugar are bonded covalently. And that means that they don't have polar bonds and they don't have ionic bonds. So they kind of share their electrons nicely. Do you know what happens when sugar dissolves into water? When sugar dissolves in water, it doesn't break apart. The atoms of carbon, hydrogen, and oxygen, they don't actually break apart, they stay together. Yes, sugar does dissolve in water, but it doesn't actually form any ions when it does that. So what does happen when stuff dissolves? There's a great YouTube video that I've posted on your class website that I'd like you to pause this video if you can and go back and watch that video. And you do have some questions on your guided notes pertaining to that. So make sure you watch that video so that you can answer the question correctly. Let's take a closer look at what exactly happens when things dissolve. Now, on the picture here, I think the same picture is in your textbook. On the left, you have 0 ions in the solution at all. Nothing has any charges. You see there's no charges in that solution here. But in the middle, you have a few ions being produced, and so you have what we like to call a weak electrolyte. But then on the far right-hand side, you see how you have many ions. You see how they all have charges on them, and that creates a light bulb to be lit up brightly, and so that would be a strong electrolyte. So ions carry electrical charge through water, so it'll complete the electrical circuit. So if you think about a wire connected to like a battery and a light bulb, if you cut the wire, you have cut the power supply, the ability for the electrons to flow through the wire. Water, when they have ions in it, does complete the circuit. You see, sugar doesn't have any ions, and so the entire compound stays together, so it does not light the bulb up. So when water actively tears apart an ionic compound or a polar compound, we call that process dissociation. Dissociation is when the water literally rips apart at the ionic compound. In this picture, you'll notice that I'm using sodium chloride. Sodium is the positive ion and chlorine is the minus ion. Take a closer look at this area right here. I want you to notice that the positive ion is surrounded by water, but look very closely at the way that water is oriented. Do you notice that there is a red oxygen that seems to be kind of sticking towards that positive ion? Well, look at this guy over here in this area. This time you have the negative ion, the anion chlorine. Now I want you to notice how the orientation of water switched. Do you notice that you actually have the hydrogens kind of sticking close over towards the negative ion? Why is that? See, I think most of you guys know that water is polar, and it makes a really good solvent. So why is water so good at doing that? Well, water is polar. That means that the electrons in the bond are not being shared very nicely. You see, oxygen has a very high electronegativity value, And hydrogen, well, hydrogen doesn't have a very high electronegativity. So that will create a slightly negative side, a negative charge kind of protruding out towards the oxygen. And since the hydrogens are having their electrons torn away from them, they're going to end up having a very slightly positive end towards them. And so that creates a uneven sharing of the electrons and also produces kind of these partial charges. That's what this silly little, it's a lowercase d or delta in the Greek alphabet. That's what this symbol is. It's kind of like a lowercase delta. So whenever you see a lowercase delta, that means that it is partially or not fully. So this is partially or not fully negative side of water. And these ends over here by the hydrogen are partially or not fully positive charge. This is just another model or view of what will happen with the water when it surrounds these ions when they dissolve in water. And you may be asking yourself, gee, Mrs. Crowley, why do you have to teach this so thoroughly? Why are we talking about this to a huge extent? Well, that's actually because I've seen AP questions specifically ask for students to draw this out. So the thing that I want you to remember is that the solvation process, it basically prevents cations and anions from recombining. It forces them to stay apart. It also disperses those ions uniformly throughout the solution. We call that the ionization or dissociation property of water. It allows water to pull those ions apart. Now, you may be asking yourself, what about the polyatomic ions? Like, so far we just looked at sodium and chlorine. But what about like sulfate or phosphate ions? Do they look kind of the same in water? Well, yeah. You can think of them as being a large chunk of atoms because they are polyatomic, and they will be surrounded in water in the same fashion. So I want you to look at this particular model that I found off of the internet. I want you to try to tell me what is good or bad about it. So take a minute to look at this before you can pause the video before you proceed on. The issue that I have with this particular model is that if this guy right here is an aluminum ion, the model doesn't necessarily show how the water molecules are going to surround that aluminum ion. Yes, this is sulfate down here, and actually this is a very nice model of a Lewis dot structure or a Lewis structure, but it also does not show how the water is going to orient itself around this guy. So this sulfate right here would probably have the hydrogens facing towards him like this, and the aluminum over here would actually probably have the oxygen facing towards him, and that's how we can maybe improve that particular model. So when we talk about things dissolving in water, we need to consider acids because acids are unique. Acids are molecules that behave like ionic compounds in water. They are able to dissociate and make ions like hydrogen ions and whatever the anion is. But officially, they are considered molecules. Fascinating. Why? Well, they're just classified as molecules, but they have polar bonds, very similar to water. So water is polar, acids are polar, so they both like to dissolve in each other. And we consider them to behave just like acids, which is kind of neat. But anyway, you need to memorize for the AP exam. There's a few things that you have to memorize, and this is just one of them. So I don't know if you've ever considered to purchase flashcards for AP chemistry, or maybe like those flashcards that are on like a ring so that you can keep them all together. But this is one of the ones that I would strongly recommend that you start memorizing. So here are your list of really strong acids and really strong bases. So it would be to your benefit if you try to memorize these. Perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. Those are your strong ones. And then just because I thought it might be also beneficial to look at, you may want to also recognize these strong bases over here. Lithium, sodium, potassium, calcium, strontium, and barium hydroxides. All right, so basically that's like your alkali metals and then some of your alkaline earth metals. All right, let's keep going. So a strong acid like hydrochloric acid, it will fully ionize and produce many ions in solution. But weaker acids, and I think I mentioned this in class, like acetic acid, they will only partially ionize. So we're kind of stuck in limbo where we have something that we like to call an equilibrium. In a traditional equilibrium, you have a forward proceeding reaction as well as a backward proceeding reaction. And in an equilibrium, you can typically tell which side the equilibrium dominates or prefers. Since we have, this is acetic acid, just written a little bit different. Acetic acid does not like to produce very many ions because it's so weak. So the equilibrium actually has a preferred side that it prefers to stay on, and that would be on the left. So the equilibrium is favored on the left-hand side. That means that, yeah, you're going to produce some of these ions, but you're not going to be able to produce very many. And so you would have a weak electrolyte, and you would not have very many ions in solution. Here's kind of a better representation of when you have a strong or weak acid. So over on the left side, you have hydrochloric acid. Let's take a look over here, this guy, okay? Hydrochloric acid will form lots and lots of ions. The hydrogen ion on the acid doesn't like to sit by himself. He actually, if he's around water, he'll produce something called a hydronium ion, which is just basically an H3O+. It's an ion. So anytime you see hydronium ions, just recognize that hydrogens in water, they don't necessarily stand by themselves. They like to kind of hang out with the water and kind of make these weak bonds with water to make an ion. And then over here you see where the chloride ion is. Okay, so that's a strong acid. Now, right here, this is acetic acid in water. You will see occasionally the hydronium ion, the H3O+, but over here you're going to have the leftover acetate ion in solution. But do you notice that you also have the complete acid, you know, this is acetic acid, that it has not been broken apart. It has, its extra hydrogen is still sitting on there. So I find this kind of a good diagram. This is a very good model. This one right here is kind of a simplified version of what you just saw on the left. This is just a different model. This right here on the top, this is kind of a model of what a strong acid will do. What you have here is like a hydrogen connected to a anion. And over on the right side, you see how all of the hydrogens and the anions are swimming around in solution separate from one another. And then in the second model down here, this one right here would be your weak acid. So you will still have some ions being produced. You see how they're separated right here? But do you also see how you have some compounds, some of the acid that didn't actually break apart? All right, so this symbol right here just basically represents a equilibrium in which we kind of have some of the ions being produced, but not very many of them. And anybody have any idea of what this compound is right here? All right, the red stands for carbon. The black one is the red ones are your oxygen. The black one is your carbon. And then these two on the ends right here, these are your hydrogens. So if you think about what that formula would be, this is H2CO3. That is carbonic acid. And carbonic acid is a weak acid. And so you see this equilibrium sign going on. Anytime you see an equilibrium sign going on, that's probably going to be a weak acid. This compound right here is actually CO2. Carbon dioxide has two double bonds between the carbon and oxygens. And then over here you have, well, water, H2O. So carbonic acid will naturally on its own decompose into carbon dioxide and water. And you'll notice that you have an equilibrium going on. So this is actually kind of a slow process. It doesn't happen very readily. But have you ever had, like, say, a soda that's been left out over a long period of time and it loses its fizz? That's because the the carbonic acid has actually dissipated and it's actually produced CO2, which escapes, and a bit of water. And the CO2 effervesces as a gas. So interesting phenomenon that we'll talk about a little bit more in detail later. So now let's take a look at a sample AP question. I mentioned that I've seen these AP questions before. I basically took some of the AP Central's released exams, and I kind of edited a little bit to share with you. So basically the idea is that you have some solid LiCl, you see the symbol S, dissolved in water, and basically you have to draw an interpretation of what the aqueous lithium chloride solution would look like. But it says base the particles in your drawing on the particles shown in the representation provided, which I did not provide for you because I didn't want to, have copyright infringement. But basically think of an LiCl compound. And then it says include only one formula unit of LiCl and no more than 10 molecules of water. Your drawing must include the identity of your ions. In other words, you should put the symbol in the charge, and the proper arrangement and orientation of the particles in the solution. So what they're talking about literally is what I showed you already, is what happens to the water when you have an ion in it. So we've already shown you that before up here, right here. So make sure that when you draw, this is like one formula unit of sodium chloride, as you can see in the drawing. And if you look very closely, I've drawn 1, 2, 3, 4, 5, 1, 2, 3. I have a total of 10 water molecules surrounded in my sodium chloride. So this would be kind of like my example of a perfect answer to that particular question. Now, in this particular drawing, they also included some of the partial charges right here on the water. So they just drew these as full charges. I think to make AP Central happy, you may want to, instead of just drawing those charges on the water, you may actually want to do that delta, the lowercase d, and go partially negative and then partially positive, just so that they don't look like full charges. Here on the chloride ion, there is a full charge, and on the sodium ion, there would also be a full charge. So that would be the only nitpicky way that I could possibly kind of change that particular drawing model. All right, we're coming into our next topic, which is precipitation reactions. This is shown in section 2 of chapter 4. So for most of us, this should be a review, soluble versus insoluble products. So the way that you can increase solubility, or the ability for the solvent to dissolve, is you can heat the solution up, you can agitate it, or you can increase the surface area of the solute by chopping it. This is something that is important right here, and so please take heed of this. Anything that has a concentration upon dissolving, or an ability to dissolve, with a maximum concentration of 0.01 moles per liter or less, is technically by definition considered to be insoluble. So I think we did discuss in class how there are some substances, when you look them up and you look up their solubility, they actually say partially soluble. And I do want to make sure that you understand that the solubility, the ability to dissolve, is not just yes or no, black and white. There is a bit of a gray area in there. There are some AP teachers out there who actually make all of their students memorize the solubility rules. Don't worry, I'm not going to do that to you. However, I think it might be important that you remember maybe just a few. How about a happy compromise? So here are some of the things that I would like you to remember. Anytime you see an alkali metal, okay, those are the elements in the first row, they are always soluble. Anytime you see any nitrate ions, nitrates are always soluble. Anytime you see ammonium ions in the front, NH4+, those are also always aqueous. And then, I think we already mentioned this, we do have some compounds that are partially soluble. So, like acids, certain weak acids. What do we do with those? So hydroxides are kind of interesting. If you look up their solubility, you will see that certain cations create this partially soluble compound. So when you're writing net ionic equations, which is a topic coming up, you may not see those particular ionic compounds that are partially soluble. You typically won't see them as labeled AQ. You won't see that. What you might see instead are the equilibrium signs instead. So double replacement reactions are sometimes called exchange or metathesis reaction. That's just vocabulary that might not be familiar to you. So when we look at these double replacement reactions, it's very easy to predict which product will be your precipitate. Just use your solubility rules. But there's something that you should be aware of. Water on the reactant side can sometimes form precipitates as well. So you need to be very careful about watching and treating water as if it were, I like to call it hydrogen hydroxide. So sometimes I'll go like this, HOH, and really what that means is H2O. So predicting your products is not too difficult of a concept. So let's do a couple examples. So a solution of silver nitrate is added to a solution of calcium chloride. And if you want to, just try to do this on your own. Pause the video right here. And let's try this. Let me show you how to do it. So you would need your cation and anion sheet kind of right next to you so that you can check the charges and all this stuff. Silver nitrate. Silver is a +1 ion. Nitrate is a -1 ion. And it does say a solution of silver nitrate, so anytime you get that keyword in a problem, you automatically know that it's going to be aqueous. It looks like this solution was added to some calcium chloride, again, another solution. So just check your charges. Calcium on the periodic table is a +2, chloride is a -1, so you're going to want to double that up, and we'll label that guy as being aqueous. So predicting your products is not too tough. What you need to do is just realize how you made that compound. So silver nitrate is a silver ion with a nitrate ion, and calcium chloride is a calcium ion with chloride ions. So when you rearrange these guys on the product side, you just need to make them have a new partner. So silver's new partner is going to be chlorine, and you need to rebalance the charges. So silver is a +1, chlorine is a -1, so there's your product right there. And your other guy is going to be calcium nitrate. Calcium is +2 and nitrate is -1. So you have to balance those charges again. So remember how I was telling you there are certain solubility rules that will assist you if you just memorize them. Nitrates, you see this guy right here on the product side? Nitrates are always soluble, so I know that this guy is going to be aqueous. And I would probably want to just double check on this chloride. All chlorides are soluble unless they have silver, mercury, or lead in them. So I know that this is my precipitate. Precipitates are insoluble, they're not able to dissolve, so we should be labeling that as a solid product, and there's your precipitate. Let's try the next one. Cobalt-2 acetate. Cobalt. Now, the cobalt Roman numeral 2 means that this is a +2 charge. The acetate ion is polyatomic, C2H3O2, and it's only -1. So I'm going to have to double that guy up, and it's polyatomic, so you'll see that I have him in parentheses. Calcium hydroxide. So calcium is a +2, hydroxide is OH, which technically is polyatomic, and he's only -1. So if I have a +2 and a -1, I'm going to have to double up the hydroxide. Alright, so matching up the products on the other side, cobalt is going to have a new buddy. Cobalt is going to go with hydroxide. So cobalt in the beginning was a +2. That means he'll be a +2 on the other side as well. So this hydroxide is only -1, so I'm going to go like this. Your other product is going to be the calcium acetate. Calcium is still a +2. Acetate is just a -1. So I'm going to have to double up the acetate, and since it's polyatomic, I put it in parentheses. Alright, like I said, certain solubility rules are pretty handy to remember. All acetates are soluble, no exception, and what you'd want to do is just kind of double check on the hydroxide. The rule for hydroxide is kind of mixed, make sure you double check it. But anyway, if you have a cobalt in there, it does make it insoluble, so this would be my solid insoluble precipitate. So obviously the next step would be to get the net ionic equation. What I did up above was just simply predicting my products and getting solubility. So I don't know if you've ever done an ionic equation before, a net ionic equation, but when we look at a net ionic equation, it does not have what we like to call spectator ions. Spectator ions are ions that did not change from the left side to the right side. They are soluble on both sides. So net ionic equations take these guys out. So in AP, one of the things that I would like you guys to know is that you can jump straight to the net ionic equation. You do not have to show, all the ions pulled apart and, separated. So if we go back to the previous example, I want you to try to identify what the net ionic equation is. While working on net ionic equations, you should be aware of some interesting exceptions, shall we say. So hydroxides are kind of unique. Calcium and strontium hydroxide are moderately soluble, and they can be written separate, like you can ionize them. They're aqueous, AQ. But if you ever see beryllium and magnesium next to your hydroxide, you don't want to have them be able to be dissolved, so you actually would want to label them as a solid. So all of the other alkaline earth metals with hydroxides may be ionized in those equations. They could be labeled AQ. So in our previous example, we were looking at silver nitrate and calcium chloride. And then in our second example, we were looking at cobalt acetate and calcium hydroxide. And the best way to do the net ionic equation is to look at what was the precipitate on the product side. In our first example, the precipitate was silver chloride. So to get to your net ionic equation, it's pretty easy. You would start off with some silver ions in solution, combining with the chloride ion in solution. And when those two find each other, they're going to make your precipitate, which was silver chloride. In the second example, it was pretty easy to identify who the precipitate was. That was going to be cobalt 2 hydroxide. So to make the net ionic equation, it's pretty easy. We would just say cobalt, and it's a positive 2 ion dissolved in water, plus your hydroxide ion dissolved in water, and then we would produce our product, which would be cobalt hydroxide. Watch those charges. So in the second example, the only thing that you have to concern yourself with is that the overall net ionic equation here is technically not balanced. On the product side, you have 2 hydroxide ions in cobalt hydroxide. So you would have to be very careful to come back and use a coefficient on that hydroxide with a 2 in the front. And then it would be a balanced net ionic equation. Although it's really nice to know that in AP exams you really don't have to do the total ionic equation, which would include all of your ions dissolved in water, like what you see right here. Even though you don't have to do that on AP exams, it's still kind of an important skill. So in this particular example, we've got silver nitrate and potassium chloride, and anything that was soluble, anything that was labeled as an AQ, is going to be broken up. So the silver separates from the nitrate, the potassium separates from the chloride, and then over here we keep that solid together. You can't break him apart. But on this aqueous product, the potassium and the nitrate would split up. So you see how the cation and anion gets split? Each species is broken into its own chunk. You see here's the potassium, there's the chloride. But when we move to the product side and you get to that silver chloride, which was insoluble, notice how we kept silver chloride together because it is a solid, insoluble. But then here's your potassium and there's your nitrate. So in a net ionic equation, we take out something called a spectator ion. A spectator ion is any ion that is aqueous on both sides. So if you go simply to the product side after this arrow, look for the stuff that is still aqueous. The potassium is aqueous, the nitrate is aqueous, and you'll notice in the reactant side that they are also aqueous as well. So once you remove those spectator ions, you will be left with your net ionic equation. So here's just a summary of how to do those net ionic equations one more time. So here's a separate example. You have, let's try it together, you have potassium phosphate being added to a solution of strontium sulfate. Step number 1 is to get that balanced formula for all of the formulas and predicting your products. Then, that's step number 2. And then step number 3 would be to go through and predict your solubility, make sure you balance that reaction, identify your spectator ions and get rid of them, and then just rewrite whatever's left, and whatever's left is your net ionic equation. So notice in this very first step, what I typically like to do is just write out all the formulas, and don't bother with any of the solubility yet. And at this point, what I would try to do is go back through and balance. Now, double replacement reactions are actually pretty easy to balance. This looks like a lot of atoms to keep track of, but instead of keeping track of the atom, why don't you try to keep track of the ion? Here is your potassium. Find him on the product side. On the left, you have 3 potassiums, and on the right, you only have 2. So a mix of 2 and 3, you may want to try to do a common multiple, like 6. So if I place a 2 in the front of this compound, that will give me 6 potassiums. In order to get 6 potassiums on the right, you would probably want to put a coefficient of 3 right there. All right, let's look at another ion here. Let's look at phosphate. I placed a 2 in the front of potassium phosphate, which means that technically I have 2 phosphates. Let's go to the right-hand side. Here is your phosphate polyatomic ion, and you'll see that there is a 2 on the outside of its parentheses. So I actually have 2 phosphates right there too. Let's find the next ion, strontium. Strontium on the left, I only have 1, but here you see I have 3. In order to balance that, I'm going to stick a coefficient of 3 in front of this, which also creates 3 sulfate ions. On the right side, you see the coefficient here, which means you actually have 3 sulfates as well on the product side. So double replacement reactions are actually pretty easy to balance. The next step that we would want to do is to look through the solubility rules. Once you have determined the solubility of all of the compounds, you can just skip straight to the point at which you identify your spectator ions. So what I've done here is I've crossed off the sulfate because the sulfate on the product side is on the aqueous product. And then here I see my potassium, so I crossed off the potassium right here on the reactants. So what do you have left? You still have the phosphate ion and the strontium ion, and then your this is the product side, sorry, your solid product right here. So you can simply simplify to your net ionic equation here, and then you're done. In AP, you usually get to skip straight through. Pretty nice, huh? So to show you how relevant this particular topic is, I thought I'd pull a sample AP question. Now again, I did modify some of the content just to make sure that I wasn't infringing on any copyright. So a student performs an experiment in which the conductivity of a 500 milliliter solution of calcium hydroxide is slowly titrated with hydrosulfuric acid. What that means is that we're slowly adding some hydrosulfuric acid to a container containing calcium hydroxide. And as we slowly add that hydrosulfuric acid, we're monitoring the conductivity of the solution. A precipitate is formed during this titration. The data collected from the experiment looks like that down there. So part A wants you to provide the balanced net ionic equation for the neutralization and the precipitate reaction. Part B, the conductivity of calcium hydroxide drops as the hydrosulfuric acid is added. Identify the chemical species that enable the solution to conduct electricity as the first 30 milliliters of acid is added. And then part C, on the basis of the answers that you have given in parts A and B, explain why the product or the conductivity decreases. All right, so my best guess on what you would want to typically start with is let's look at the reaction. Let's look at the balanced reaction. So up here it says that we have calcium hydroxide being added to hydrosulfuric acid. So let's check what that looks like. Calcium hydroxide, we already looked at that formula, and it does say that it is a solution, so I'm going to go ahead and automatically put an AQ, is slowly titrated with hydrosulfuric acid. So if there's a hydro on the front of the name, that means that it came from a monatomic ion from the periodic table. And it did call this a solution, so I'm automatically putting an AQ. All right, let's predict what those products would be. Calcium is going to have a new buddy. Calcium is going to want to be with the sulfur ion right here. We call that sulfide. So this will be calcium sulfide. Calcium is +2 and S is -2. Now what's left is the hydrogen in the front of the acid and the hydroxide on the back of calcium hydroxide. So what would a mixture of hydrogen ions and hydroxide ions give you? And this is part of that thing that I told you would be very important to remember. Hydrogen hydroxide is actually water, liquid water. You see, this is a neutralization reaction. This compound right here is containing a hydroxide. Hydroxides are typically classified as a base. And then obviously this guy has the hydrogen in the front, he is an acid. So typically when you add an acid to a base, you will be producing water in a neutralization, reaction. All right, this isn't quite balanced yet until I get a 2 in front of my water. All right, so we're set. Part A wants us to provide the balanced net ionic equation for the neutralization and precipitation reaction. A neutralization reaction typically involves the formation of water. So I would actually provide two different answers to this question. One for the neutralization. In the neutralization, we would simply have hydrogen ions, H+, combining with hydroxide ions, OH-, to produce liquid water, H2O, liquid. And that would be one of my net ionic equations. The next one wants a net ionic equation for the precipitation. So that must mean that this product right here produces some kind of precipitate. And you can check your solubility rules, but that is a insoluble product. So for this guy, we're going to have calcium ions dissolved in water, combining with the sulfide ions in water. And when they find each other, they're going to make that insoluble product, calcium sulfide. Okay, so let's keep going. Part B. The conductivity of the calcium hydroxide drops. All right, so over here, this solution started off as pure calcium hydroxide. And as time went by, obviously, the acid was being added to that. And as time went by, as you can see, the conductivity was dropping. It was coming down. I guess the reason why is because look at what you're forming. You're forming a solid precipitate, and solid precipitates can't produce any electrical current or can't conduct any electrical current. And pure water is not an ion, therefore he can't conduct electricity either. So it wants to know what the identity of the chemical species that enabled the solution to conduct electricity was to begin with. So here is your calcium hydroxide. When that dissolves in water, you will be making calcium ions and hydroxide ions. So for this answer, all you would have to say is calcium ions and hydroxide ions. For the last part of the question, part C, all you have to do is provide an explanation for why the conductivity decreases. You should be able to say in two parts that basically the precipitate is being formed and precipitates are insoluble. And finally, if you would like any help with double replacement reactions, net ionic equations, or maybe you just want to kind of practice or quiz yourself, I've got some great links. I'll make sure that they're posted on the class website for you. That concludes part 1 of chapter 4.